Hi guys, this is the second part of the P8 Forces module. Here is a recap on the key terms and ideas that you need to know prior to starting this topic.
So I just want to look at another idea around forces, which is Newton's third law. And this is that when a force is applied between two objects, there is an equal and opposite force, which you may have heard as a phrase before, that there are equal and opposite forces. Now this seems simple enough, but it can be tricky because you need to be really precise on where you're looking within a system. So we'll just look back at a couple of our examples to show you what Newton meant by his third law of equal and opposite forces. So previously we looked at an object on the desk and it was being pulled by a force of 5 newtons, and this idea of equal and opposite forces is to consider the specific contact point. So if we look at the point at which this string, which is being pulled by a person, say, is in contact with the object, what we have is object itself is being pulled with a force of 5 newtons, so not drawn to scale, that's going to go to 5 newtons. But at the same point, you could consider that the person who was pulling the object would feel 5 newtons in the opposite direction on their arm, and that really is it. So where do the misconceptions and difficulties lie is when we look at the wider system. So if I just redraw that, and what we had was that the object had friction of 2 newtons in the opposite direction, and I think, and basically that's where the difficulties lie, because people think that that is the equal and opposite force, but you have to realize that it is a completely different force, and that's why it's really important to label them. So by labeling it the pull force and the friction force, you kind of break that problem down so that we can see that the equal and opposite force is right there, and the equal and opposite force of the friction is here. So what is going on at this contact point is that if we look at if we basically going to separate the box, so if this is the box there, we make it jaggedy, so we're magnifying that up, so it's the rough surface of the box, and then I'm separating it with the rough surface of the table. What we can see is that this 2 newtons of force on the box here, again not drawn to scale this time, just to make it fit on my diagram, so we've got 2 newtons of force from friction all along the surface of the box, and the equal and opposite force from the friction is actually felt by the table. So there you have 2 newtons almost dragging the table along, and that was Newton's third law, that you do have an equal and opposite force at the contact point, but when you're looking at the complete system, it doesn't mean to say that the friction has to be equal and opposite to the 5 newtons of pull. And the key is to label it and to realize that the pull is a different force to the friction, which I know it sounds really simple. Where it's important is when you appear to have equal and opposite forces. So a third little example. So here we've got, again, 5 newtons of force. Imagine if we had 5 newtons of friction. We're going to find our resultant force by combining the two. We can combine them because they are 2 different forces. So we've got 5 newtons in this direction, 5 newtons in this direction, so we're going to have 0 newtons resultant force. So that is the resultant force. It is the single force that these 2 individual forces cause to occur on the object, but it's because of the equal and opposite forces at the contact points. So there's an equal and opposite force pulling on someone's arm of 5 newtons here, and there is an equal and opposite force of 5 newtons of friction on the table, and then we can look at the single object, and that is 0 newtons resultant force, and we call these free body diagrams. And what the free body diagram is you are actively making a decision on what is the object, what's the body that you're interested in. So that is Newton's third law, that when a force is applied between two objects, then there will be an equal and opposite force at the point of application. So the last thing that I want to bring to this video is how we represent weight and how that is closely related to mass and centre of mass. Now, you know, especially if I'm your physics teacher, that I will bang on about how weight and mass are totally different. So just to revise that, weight is a force and it is due to gravity. And mass is measured in kilograms, and a simple way of looking at it is how much there is of a substance. That is a very simplified way of thinking of it. There are more complicated ways of looking at mass, which I'm not going to get into today. When we talk about the centre of mass, what we're doing there is looking at an object and then considering the single point at which all of the mass can be thought of as being concentrated. And basically it simplifies force problems so that we can represent forces and their action on objects much more simply. So if we consider some object, and this is a fairly massive object, then we need to think, well, if we're going to analyse the forces, I'm not really interested in the ins and outs of the shape itself. And actually what I want to do is just consider a single point which we call the centre of mass. And it's then much more easy to apply forces to it. So if I take that centre of mass as a dot, I can then consider any weight. I could consider the ground pushing up, or any other forces that I wanted to put on the object. It just simplifies things. So there is a method of working out where exactly the centre of mass is, and basically that method is to think about where the object hangs. So if we were to take, let's say, a random shape and then to suspend it on a bit of string, and then get a pen or a pencil and draw a line right down the object following the line of the string, then the centre of mass must be on that line at some point. So if we've suspended it here, and then I take the object again, obviously it's not the exact same shape because it's just a random object, and suspend it again and draw my line again, the centre of mass is at the crossing point. If it's a random object, so if it's a random shaped object, that is how we find the centre of mass. If it is a symmetrical object, so if there's symmetry, then we can use that to predict what the centre of mass is on the object. So if I draw lines where there would be symmetry, then I can work out where the centre of mass is. So if you've got a random object, then you need to suspend it and look at where the centre of mass would be. It's where the weight of the object would go straight down following the line that you were suspending it by. Repeat the procedure, so hang it somewhere else and do it again, and then you'll see again that the weight, which is the force, remember, the weight will act on that line. So the crossing point is the centre of mass. If you've got symmetry, then the object you can find where the centre of mass is by using that. So you just draw the lines where there is symmetry, and where it crosses, you found the centre of mass.
So that's the end of the forces video. Please make sure you email your teacher if you're struggling with any of the ideas or you need any further support.